In this lecture, we look at simple AC circuits. The first circuit has a resistive load. We have an AC source, which has an amplitude of V0 and a sinusoidal oscillation of sine omega t. Omega is the angular frequency. This drives a resistor with resistance R. That's the resistive load. Ohm's law holds for a resistor, so the voltage drop across the resistor is minus I of t times R. There are only two elements in the circuit, so we have that I of t times R, the resistance, is equal to V of t, which is equal to V0, the amplitude, times sine omega t. Now I of t then is equal to V of t divided by R. And plugging in the value for V of t, we have it equal to the amplitude V0 divided by R times the sine omega t. And if we write this as an I0 times sine omega t, that means the amplitude of the current is I0 is equal to V0 divided by R. So the current amplitude I0 obeys something that looks like Ohm's law also. Also, the phase delay is 0, so phi is equal to 0. So if we look at how the current and voltage behaves, the driving voltage is the red curve, and the blue curve is the current. The current is in phase with the voltage. That's the main result of this simple circuit. The second simple circuit, it has a capacitive load. It's the same driving voltage source driving a capacitor with capacitance C. Capacitors don't obey Ohm's law. Instead, we've seen that delta Vc is equal to minus the charge Q divided by the capacitance. But there are only two elements in this circuit, so V of t must be equal to Q divided by C. We also know that the current is the derivative of Q. So if you write down I of t is equal to dq dt, and then plug in what we know for Q, that it's C times the V of t, and take the derivative, we get that we can pull out the C, take the derivative of V of t, the time-dependent part, and the derivative of V0 sine omega t is omega times cosine omega t. So we have C times V0 omega cosine omega t. We want to put this into the standard form for the current, where there is some I0 current amplitude times the sine of omega t minus a phase. That means the current amplitude is equal to omega times the capacitance times the driving voltage amplitude, V0. I0 obeys a relation like Ohm's law, just like we saw in the first circuit, if we let I0 equal to some V0 divided by XC, where XC is equal to 1 over omega C. XC is called the capacitive reactance, and it acts like a resistance, and it also has units of ohms. The phase is minus 90 degrees, since cosine theta is equal to sine theta plus 90 degrees. This means that the current leads the voltage in a capacitive circuit. And we can see this on the plot. Again, we show the red curve, which is the voltage of the driving source. And the blue curve is the current. And we see that the current leads the voltage as it goes up before the voltage goes up. If we look at what's happening to the capacitor at the various points A, B, C, and D, we can see that at A, there's a current flowing onto the capacitor, though the current is, and that's where the current is at a maximum, but there's no charge in the capacitor. At B, the capacitor is fully charged, but there's no current flowing onto it. The current is 0. At C, the current is now flowing in the opposite direction, and there's no charge in the capacitor. Finally, at D, the capacitor is fully charged, there's no current flowing onto it, but the charge is now opposite of what had happened in point B. Our third simple circuit looks at an inductive load. That is, we have the same driving voltage, but now it's driving an inductor with an inductance of L. Inductors don't obey Ohm's law. Instead, the voltage drop across an inductor is equal to minus the inductance times the time derivative of the current. So, since there's only two elements in the circuit, V of t must be equal to the inductance times the time derivative of the current. If we want to find I of t, then we're going to have to do an integral of V of t. And that's equal to 1 over L times the integral of V0 sine omega t dt. Once we do an integral of the sine omega t, we end up with minus 1 over omega L times V0 times cosine omega t. We rewrite this in terms of a sine to put it in our standard form, and we have V0 divided by omega L times sine of omega t minus 90 degrees. So if we pull out the current amplitude is equal to V0 divided by omega L. And again, it has an Ohm's law relationship where I0 is equal to V0 divided by some X sub L. This X sub L is now the inductive reactance, and X sub L is equal to the angular frequency times the inductance, L. Again, the units of this are ohms. The current lags the voltage by a phase of 90 degrees. So that if we look at the plot of the two curves, the voltage driving the circuit and the current in the circuit, we see that the current is following the voltage by 90 degrees. One way to look at this, at this lag, is that the inductor tries to make a backwards voltage that is proportional to the time derivative of the current, and this stops the current from flowing. Let's look at some examples for calculating reactances. First, what is the capacitive reactance of a 10 microfarad capacitor driven with different frequency AC sources? We'll calculate X sub C for 60, 120, and 600 Hertz. X sub C is equal to 1 over the angular frequency times the capacitance. We need to write this instead for the regular frequency, so that is 1 over 2 pi times F times the capacitance. So the capacitive reactance for a frequency of 60 Hertz is equal to 1 divided by the quantity 2 times pi times 60 Hertz times 10 times 10 to the minus 6 farads, and that's equal to 265 ohms. X sub C for 120 Hertz is equal to 133 ohms, or half the original value for 60 Hertz. And X sub C for 600 Hertz is 26.5 ohms, or 10 times lower than the value for 60 Hertz. So generally we see that the capacitive reactance decreases as frequency increases. Second, what is the inductive reactance of a 10 millihenry inductor driven with different AC sources? Again, we'll calculate X sub L for 60, 120, and 600 Hertz. So the inductive reactance is equal to the angular frequency times the inductance. Again, converting that into the ordinary frequency, it's 2 pi times F times L. So X sub L for 60 Hertz is 2 pi times 60 Hertz times 10 times 10 to the minus 3 henries, which is equal to 3.77 ohms. X sub L for F equal to 120 Hertz is equal to 7.54 ohms, or twice the value for 60 Hertz. And X sub L for F equal to 600 Hertz is equal to 10 times the value for 60 Hertz, or 37.7 ohms. So that the inductive reactance increases as frequency increases, opposite to the behavior of the capacitive reactance.